Thank you, Rosie, for the time. I come back again. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. Good morning, ladies and gentlemen. So this will be our very first plenary session, in which will be delivered by Professor Dr. Anne-Marie Hirt and Professor Dr. Wahyu Sri Gutomo. Firstly, Professor Anne will have 30 minutes to deliver her talk and 10 minutes for Q&A session. And afterwards, the opportunity will be delivered to Dr. Wahyu Sri Gutomo for 20 minutes presentation and 10-minute Q&A session. But ladies and gentlemen, now allow me to give a very brief introduction for Professor Anne-Marie Hirt from ETH Zurich. So the moment we know this greatest city in Switzerland, we will eventually remember one of the most or greatest scientists in the world, Albert Einstein. And Albert Einstein also spent some time of his life also in Zurich, in ETH also. Anne-Marie Hirt was awarded the title of professor at ETH Zurich in 2009, and she teaches in the Department of Earth and Planetary Sciences, and since 2003 heads the Laboratory for Natural Magnetism, or LNM. As a member of the group Earth and Planetary Magnetism in the Institute of Geophysics, she leads several multidisciplinary research projects. And her research interests are focused on the application of magnetic properties to various problems arising in the earth and environmental sciences, as well as the life sciences. She also investigates the magnetic mineralogy of brain and tumor tissue to gain a better understanding of their role in neurological diseases. And from the Scopus database, Professor Anne has more than 3,500 citations from 155 documents by author with H index of 35. In simple words, she is one of the most productive women professors in Zurich. And today she is here to share her expert opinion on magnetic techniques applied to material, life, and environmental sciences. Now, without further ado, ladies and gentlemen, please welcome Professor Anne.
Thank you very much for the introduction. I'd like to thank my hosts for inviting me here. It's a great honor to be here with you today. It's my first time in Indonesia, and it's a wonderful country. The talk I'm going to give you today is going to be on, as you can see, rock magnetic techniques in the material, life, and environmental sciences. And I might go a little longer, so I might cut it short. But I want to show you what you can do with methods that you've been using for rock magnetism. You can also use them in other sciences as well. And we have an advantage. When I work with people in these other sciences, they come and they think the materials are pure. You know, I bring you magnetite, I bring you maghemite particles. But in the earth sciences, we're used to, as one of my physics friends said, we're used to garbage. We don't have pure magnetite, we don't have pure pyrite or something. We usually have a mixture of things, and it's our job to try to figure out what that mixture is. So, to go on, I bring the first thing I want to show you is what our lab looks like. Do I have or how can I, is there a control for the computer, or will you go one? Next slide. Doesn't want to work. Good Swiss technology. So what I want to show you first is an introduction to our lab. Our lab is the ETH is in the city of Zurich. Our lab is still in the city of Zurich, but right on the boundary. And if it works, you'll see we're in the middle of a forest. Okay, while they're sorting out the technical problems, first I'd like to say to the students here, feel free to raise your hand or wave your hand if you have any questions, because you're here to learn. And learning is one of the most wonderful things in the world. And I'm saying, even though I'm retiring right now, I'm still learning. And I love to work with students because they teach me so much. And sometimes I'll say, oh, this is a stupid question, but there is no such thing as a stupid question. There are only good questions because they make us think further. So please do not hesitate to, go like this and ask a question. Okay, there we go, we're getting there. The other thing is, how many of you know first order reversal curves, Forc? How many know the method Forc? Do you know it? One? Okay, so I'll spend a little bit of time maybe talking about those so that you understand them. Okay. Maybe can you turn this light off? So as I said, our lab is in the middle of the forest. You can see here, you have to walk up a nice little road through the woods, and here's our laboratory here. And the laboratory was based on the very first paleomagnetic laboratory in Newcastle. It was also a nice wooden building. Try to use as little magnetic material as possible, so all the nails were made out of bronze. All the metal tends to be aluminum, so it's very non-magnetic. Next. This is a picture of the main research hall. So what we have is we have a lot of our high field instruments on one side. I'll come back to those in the middle. Next. This is looking in the other direction. We have a shielded room here. Next. And in our shielded room, here you can see a long core cryogenic magnetometer, but we also have an Agico susceptibility bridge and ovens for doing thermal demagnetization. Next. Here you can see we have instruments to measure hysteresis, and I'll be showing you a lot of measurements today from a vibrating sample magnetometer and an alternating gradient magnetometer. And this instrument here is a unique instrument. It's a high field torsion magnetometer, and I think we're the only one who has one of these instruments in the world. So I'll come back and talk a little bit about that later. Okay, next. Okay, we like to think, I was going to say the people in rock magnetism, we like to think these methods are our methods. We measure magnetic susceptibility, we measure magnetic hysteresis. But if you just do a quick survey through the literature, and I just picked the last 20 years, and you look up magnetic susceptibility, the group that uses magnetic susceptibility the most are chemists, and then the physicists, and then the material scientists. And the earth scientists only make up 10% of those 50,000 citations for magnetic susceptibility. And that was a real surprise for me, because I would have thought, we're the ones that use it most. Magnetic hysteresis, this was less of a surprise. The physicists definitely use magnetic hysteresis a lot, but then material science, engineering science, because of magnetic recording, and we only make up 3% of the literature. First order reversal curves, physicists make up half of it, material science about a third, and we're a little bit better, 14%. And the only method that we tend to use more than any other group is acquisition of isothermal remnant magnetization. And I find that a shame because I think this is the most sensitive method to detect ferromagnetic minerals. Okay, next. So what are these other groups using it for? So under material science, which would also include probably physics and engineering, of course, magnetic recording, thin films. That was where a lot of our information and the techniques were developed. Then there's sensor technology, so making a magnetic actuator. There are nanowires and nanoparticles, and these are being made more for these other applications. In life sciences, Magnetic imaging is very important today for determining a lot of diseases. Drug targeting, I'll talk a little bit about this later. Hypothermia treatment, I will talk about in a few minutes. Or blood purification. So we were working with one group within the ETH in a startup company. So if you have some sort of contaminant in the blood, what they do is they take a magnetic nanoparticle, they cover it with some sort of enzyme or chemistry that will click on to that contaminant, and then just like dialysis for liver treatment, they'll circulate the blood, they'll put the magnetic particles in, the magnetic particles with the chemistry will link onto that contaminant, and then they'll circulate the blood out of the body through a separator to pull out those contaminants. In the environmental sciences, we're going to be seeing posters and talks today with applications for pollution, for showing environmental conditions, for looking at climate, and also it can be used for looking for how effective is water and soil remediation. Okay, next. So what kind of information are we looking for when we use these magnetic methods? Well, I always say there's three pieces of information we can get. We can get composition of the iron mineralogy. So is a material pure? And as I said, usually when the chemists or material scientists come to me, they say, here, I have generated a magnetite particle. And then we measure the hysteresis and we say, it's not magnetite. It's probably oxidized, it could be something else. So has it undergone alteration? We can look at what is the composition of the phase that they're giving us. Concentration. So we can use magnetic properties to estimate what is the concentration of an iron mineral in a material. And granulometry. And here I talk about effective particle size, because we might make a nanoparticle on the order of 20 nanometers, but if they cluster together, and I have 3 or 4 particles together, it's not going to be 20 nanometers, it's going to be much, much larger. So what kind of methods can we use to look at these properties? Okay, next. Okay, just very quickly, magnetic hysteresis. We have the property saturation magnetization. We have remnant saturation magnetization, and we have coercivity. And the other property we can look at is right at the very start, we can look at what we call the initial susceptibility. So the part where we just put the field on very low, and it's reversible. And then later, using another method, we can get the remnant coercivity. That's the field we need, so when we turn the field off, the magnetization goes back to 0. Okay, next. And hysteresis, the shape of the curve is going to give us information because we know superparamagnetic curve will have no coercivity. The magnetization relaxes faster than we can make the measurement. So we'll get a curve that looks like this. Okay, next. Now there's another method you can use with hysteresis to look for interaction between particles. And this is called the transient energy. So I can take my sample, I can put on the maximum field, turn the field off, and then I can start to the hysteresis curve, the initial curve. Get this right? So I can start, I turn the field on, turn it off, and then I start up like this, go to saturation, and I will come back. Now, if I have a perfect single domain grain with no interaction, or if I have superparamagnetic, then my curve will start here and it'll trace up here and come back. But if I have interaction between my particles, then I will usually come up on a lower path here, and when I come back, it'll be on a higher path. And the area between those two curves can give me an indication of how much interaction I have between my particles. Okay, first order reversal curves. Now the reason we do this is going to be what we call a series of partial hysteresis curves. And the idea is, when we have a rock, we don't just have one grain size, one material, all in the same direction. But even if I had a bunch of grains with this size and this shape, they're not always going to be in the same direction. So I'm going to get a different hysteresis group if my field is like this and my grain is like this, or my field is like this and my grain is like this, that's going to have a role. So sometimes I'll get one curve, just for a simple example. I can have one curve with a big open hysteresis loop, if I assume I have a uniaxial single domain particle. I might have another one because it's a little bit smaller grain size. It'll have another square loop, a different coercivity. Or I can have something with even a smaller coercivity. And what I measure when I measure a hysteresis loop is I measure the sum of all of these together, all three of these together. So I might get something that looks like this. But in reality, what I have is a whole range of different hysteresis loops. Okay, next. So this is what it would look like. I would take my sample to saturation. I would come back to some reverse field, and I would come back up, go back to saturation, come to the next curve, come back up, and keep coming back and forth. Always going back to increasing my reverse field even further back, and then tracing myself up like this each time. Okay, next. And what this is going to give me is it's going to give me a whole series of points, because along this curve I have different measurement points like this. Next. If I'm down here, I can see the slope of the line of my hysteresis loop from curve to curve is always the same. So maybe my last curve looks like this, the next to the last looks like this, the next to the last looks like this, but they all have the same slope. So in principle, what this is telling me, my magnetization is saturated, it's reversible. It's not contributing to the hysteresis, to that open loop. But if I come up here, I can see my slope of my curve from this one to this one to this one is changing. And this is what causes my loop to be open, my hysteresis loop to be open. It's this change in coercivity. Okay, next. Oh wait, let me go back. Sorry. And so what I'm interested in is what I'm going to be looking at is I'm going to be looking at whatever this reverse field is, here, here, or here, and I'm going to be looking at some point. And I'm going to be looking at the change in slope between this point to this point to this point to this point to this point, so all around. Okay, next. So let's look at this. If we had like one single particle, how it would look. If I have one single particle and I have the magnetization along the easy axis, I would go up like this. I would hit the coercivity. I would magnetize it. It would saturate. I would come back until I hit the coercivity, the field in the opposite direction, and it would come back like this. So let's just say this has a coercivity. On this side, I have +1. On this side, I have -1. Next. To get the average coercivity is very simple. The average coercivity is just my +1 here minus my -1, which gives me divided by 2 and 1. So my coercivity of that material is 1. Now if I want to know the interaction field, are these particles interacting with one another? What I'm going to use is now my HA plus HB divided by 2. So I have -1 plus 1, which gives me 0, so I have no interaction in this case. Next. Now, when I have interaction between two particles, what happens is my loop shifts a little bit, either to the left or to the right, depending on whether the interaction is positive or negative. And in this case, I come up here, I switch, but no longer at 1, but at 1.5. And when I come back, I come down at -0.5. Next. So in this case, my coercivity is now 1.5 minus my 0.5 divided by 2. So my coercivity is still 1. And that hasn't changed, it's just my loop is a little bit shifted. But my interaction field now is -0.5 plus 1.5 divided by 2. So now I have an interaction field of 0.5. Next. And that would look like this on a Forc diagram. I have my coercivity here. It's 1 in both cases, but in one case, the interaction field is 0. And in the other case, the interaction field is 0.5. Okay, next. So in principle, what I'm going to be doing is a second order derivative because I'm looking at the change of slope. And I will get, this is my reverse field axis, this is my applied field axis, and I'm going to translate this with the second derivative into the interaction field on this axis and the coercivity on this axis. And usually the physicists plot it in this coordinate system, but in the earth sciences, we plot things in this coordinate system. So you can see here I have something that has a range of coercivities going from 0 to about 30 millitesla. Okay, next. And this gives us the distribution of coercivity along this axis and interaction along this axis. So in this case, this is a case of magnetotactic bacteria. What I have is very, very low interaction because the particles don't interact with one another, just along the chain. Okay, next. Now there's more information you can get out of a Forc diagram. And one thing you can get out is you can get out what part of my signal is irreversible, that means what is contributing to the open hysteresis loop, and what part of the material is reversible. So this is an example of magnetosomes from a bacteria. The grains are, most of them are above 25 nanometers, so they fall in the range of single domain. And you can see I get this nice Forc diagram here with an average coercivity of about 10 millitesla. For these kind of bacteria, they make a little bit wider grain size, so there's some finer grains under 25 nanometers and some larger grains over 25 nanometers. So in this case, what you see is here you see the reversible part of the signal, the blue curve, and the red curve, the irreversible. And here, in this case, both are similar. What I should have said here, in the ideal case of single domain, you would expect the reversible part to be 50% of the irreversible part. And so this is a beautiful example, where I say physics works. This is the theory, it says this is what you should get. The reversible part should be 50% of the irreversible part, and it is, so that's great. When we go to another type of bacteria that produces finer grains, you can see the irreversible part is much, much smaller than the reversible part. And this strain of bacteria makes mostly superparamagnetic particles, and so most of our signal is reversible and very little is irreversible. So this is very powerful information in the materials sciences if they really want to check, are there particles in that superparamagnetic range? Okay, next. Probably you're very familiar with IRM acquisition curves. You can start something with, you can demagnetize it, have no magnetization, you put it in a DC field, and you slowly acquire magnetization. And then the shape of this is going to tell you something about what material you have. So magnetite, hemite will acquire magnetization very fast in low fields. Pyrrhotite, I can use the German spelling here, you need a higher field, 500 to 600 millitesla. And hematite, with hematite you'll see it's very hard to magnetize in small fields, but then it'll start to increase. But you need very high fields to saturate it. You usually need 2 to 3 to 4 Tesla in order to saturate the hematite. Okay, next. And this is another way, this is called backfield. Essentially, we magnetize the sample in one direction, then we apply a field in the other direction. And again, you can see, you can get, from this point here, you get the coercivity of remnants. Okay, next. So in summary, just for the methods, with hysteresis loops, we can get information on the composition from the shape of the loop, and from the saturation magnetization, and from the coercivity. For the concentration, if we're looking for concentration, we can use magnetic saturation, MS. For particle size, we can use the coercivity, or also remnant saturation magnetization is good. And we can also get an idea about interaction from the transient energy field. In Forc diagrams, the coercivity spectrum is going to tell us something about composition and also about particle size. And we can also get that from this reversible, irreversible part of the sample. But what's nice about Forc is we also get more direct information about interaction between particles. And with the IRM method, we get information on composition from the shape of the curve and also from the remnant coercivity, and we get concentration from the remnant saturation. Okay, next. Okay, so any questions so far? That was just a quick review of something I hope you also had in your lectures. Okay, so some examples from materials science. In this study here, we were approached by a group from the University of Freiburg in Switzerland, and they were making hematite nano spindles. And these hematite particles they were making, these things are about 250 nanometers long and 50 nanometers wide. And what they wanted to do is they wanted to reduce these to maghemite. And so what they would do is they would put them in a reducing atmosphere and then see if they could tune their particles so you could get a composition somewhere between hematite and maghemite. And it was very interesting because what they found was, here's your hematite particle here, and it wasn't that the maghemite or magnetite formed throughout the whole spindle. You actually got these like stripes. So this is your magnetite here, and this is then hematite. And then with higher amount of reduction, you see the magnetite is here and here, so you start getting bigger and bigger swatches or patches of this maghemite magnetite compared to the hematite. And they wanted to know how successful their conversion was. Because, you know, to do TEM pictures, that takes a lot of time. So next. So we said, well, why don't we try some magnetic parameters to see how good? Because we know hematite has a very low susceptibility, low magnetization, and magnetite, maghemite, has a high susceptibility, high magnetization. And sure enough, you can see here is the susceptibility. The starting one has a very low susceptibility, and as they reduced the sample, it got higher and higher. So they got a nice linear relationship for the amount of magnetite or maghemite and the susceptibility. The same is for the saturation magnetization. So again, you can see that they got a steady linear increase in the saturation magnetization as they converted the hematite to magnetite maghemite. The same for the remnant saturation, a nice linear increase. The one that didn't work so well was coercivity, and that's a little bit more complicated because it's going to be strongly dependent on the particle size as well, not only composition. Okay, next. Now another thing this group is, and actually this was the first study when they came to me, they had made these spindles here. And these things, okay, they're 250 nanometers long and 50 nanometers wide, hematite. So what would you expect its domain state to be? For hematite, that should be single domain. And when they measure their hysteresis loop of the uncoated sample, you see it had a very, very low coercivity. And hematite should have a very high coercivity. So they were very puzzled by this. And then we said, well, maybe there's interaction going on. So then the next time they coated their particles. And what really surprised us is rather than the hysteresis loop got bigger, it got smaller. And then it was actually closed. And we said, okay, this is really strange. So what's going on with this system? Okay, next. Well, we thought, okay, let's first measure some Forc diagrams. And this is a nice example. These are the uncoated particles. You see you get a range of coercivity like this, and you get things very close to the origin like this. In the uncoated, you lose all the higher coercivity, and you just have something here at the origin showing that your loop is closing. But what was interesting is you see this density patch here, it's above 0. And that's telling you it's very, very common for what you find for superparamagnetic particles. Okay, next. So we said, okay, if it's superparamagnetism, then maybe time should be playing a role. So in this case, we measured at 1 second averaging time, and then we remeasured it at 0.1 second, 100 millisecond. And you can see what happens is the Forc distribution comes out this way. So we have, because we're measuring faster, if our sample is relaxing, then we should see more of the signal because part hasn't relaxed in the 100 millisecond, that has relaxed in the 1 second. Okay, next. So if you go back to how they make these particles, they start out with very fine particles on the order of 5 nanometers, and then these 5 nanometers aggregate together, and then they call something called ripening. So their idea is those aggregates of particles all come together and form one big giant hematite crystal. But in reality, that's not what happened. Next. you can see from this high resolution TEM picture is, yes, you have hematite, and if I go from this point to this point to this point, I get the same diffraction pattern. So all these little islands of hematite all have the same orientation, but there's enough distance between them so that it's a series of superparamagnetic grains. So grains on the order of this 5 to 6 nanometers, with enough space between them that they preserve their superparamagnetic behavior. Okay, next. So just some examples from material science. Now let's look in life sciences. And again, this is more materials, but then it's going to be used for a life science application. Next. And one is drug targeting. This is becoming very important today. It's a giant industry. At one point I did look at the statistics, but I don't know. I mean, the industry is in the billions of dollars. And the idea here is, how do you do cancer treatment? Let's take the example of a tumor. So what is done is you introduce a chemotherapeutic material into the bloodstream. This then circulates through the body, and the idea is tumors use a lot of blood. They take up a lot of blood. So the idea is that the chemotherapeutic drug will be taken up to the cancer, but it's essentially circulating through the whole body. And for this reason, they have to use fairly high doses because you really want to get enough of that drug to the tumor itself. But what happens if you would take a magnetic nanoparticle and you would coat this with the chemotherapeutic material, and then you could put a magnet close to the area where the tumor is, and then when the material or the drug goes through the bloodstream, it gets captured more by the tumor. And this has the advantage that it would allow you to use less of the drug, less chemotherapeutic material than you would if you just have to keep letting it circulate by itself through the drug. And that's less toxic for the body, because that's the problem. These drugs are highly toxic. Okay, next. So we worked with one group. What they were using for their magnetic nanoparticle was an iron-3 carbon cementite. It's on the order of about 30 nanometers. Next. We wanted to look at the magnetic properties of this cementite. The advantage of this mineral is it has a very high saturation magnetization. So if you know magnetite, it has a saturation magnetization of 92 kiloamperes per meter. Cementite has 120, so it's about 30% higher. It also has a fairly high remnant coercivity. Okay, next. So the first thing we did is we wanted to make sure that how does it scale? We want to know how much of that drug or the nanoparticles are reaching the tumor. We wanted to know, can we actually look at this? So my student prepared, it was part of a master's thesis, he prepared different concentrations just of this nanomaterial itself. So we had 3.8 milligrams, 1.6, 0.8, and 0.3. We measured the IRM acquisition curve. We got the saturation remnant magnetization. We also were able to check the remnant coercivity of the material. And then what we could see is this remnant saturation concentration as a function of mass. That gave us a calibration curve. So later when we measured the tumor tissue, if we measured this remnant saturation, we could tell them how many particles were actually in the tumor. Okay, next. So this is an example of the experiment. You can either do in vivo, that means within the animal or the person, or you can do in vitro. This was an in vitro experiment done on rat liver. So they would take the liver out of the rat. They would actually put it in here. They would hook it up to a bloodstream, so essentially the liver would be functioning as if it was in the rat. It would produce bile. So it was a normal thing. Then we could introduce the nanoparticles into the system and then check to see where they were accumulating. So this is a liver before it had been treated with the nanoparticles, and this is the liver after it's been treated by nanoparticles. And a liver has 4 lobes. It has 4 different parts. And so what they did is they would separate it into its 4 different parts. Okay, next. Here you see some IRM acquisition curves for 2 of the livers. Liver 3, where we have lobe 1, 2, 3, and liver 4, lobe 1, 2, 3. In liver 4, they just put a magnet close to the liver, but not close to a particular area. And you can see from the bluish curves here, you get slightly different values, so the nanoparticles are not distributing homogeneously throughout the livers, but they are being delivered. In the case of liver 3, they actually tried to put the magnet close to one side of the liver, so you can see that 2 of the samples had a high IRM, and 1 sample had almost no. So the one furthest from the magnet did not actually collect any particles. So that was a good thing for them, for being able to target very accurately. Okay? Okay, very similar treatment is called hypothermia treatment. And it's very similar to the drug targeting, but this case, what you do is when you deliver, actually it's done very often in combination with the drug targeting. Once you deliver that material to the tumor, you apply an alternating magnetic field. And what happens when you apply an alternating magnetic field? You'll start to move. So there's 2 different types of motion. If this is my nanoparticle, either my whole particle can flip back and forth, that's called Brownian motion, or my particle doesn't really move, but the magnetic moment in that particle flips back and forth, that's Snell. And very often in these superparamagnetic particles, what you have is a Snell magnet or motion. Okay, so your magnetic moment's flipping back and forth, and what happens when your magnetic moment flips back and forth? Very good, you generate heat, okay? And what's really interesting is you will kill off a cancer cell tissue when you reach 54 degrees Celsius. So not much higher than what your body temperature is. So the big quest in the, let's say in the industry looking for this hypothermia material is what materials generate the most heat in the lowest field, okay? So I'll give you an example here, one example. It's a little bit low, but what you can see here is the student was making materials with many different grain sizes, many different compositions. What you see on this axis is the change in temperature. So he could get anywhere from almost no change up to a 40 degrees Celsius change in the material, in the nanoparticle itself. And what he found is if you plotted against the coercivity measured from a hysteresis loop, you saw that the highest heating were coming from the ones with the lowest coercivity in most cases. But there were also particles here with low coercivity that did not generate much heat. So what he found was that these particles here had a very low saturation magnetization, where these particles here had a very high magnetization saturation. And so he developed this parameter where he took saturation magnetization divided by coercivity. So if coercivity goes to 0, this value will become high. And he found a nice linear relationship between the raise in temperature and then this parameter. So this then they now use as a guide for how well would the material behave. Okay? Next. I'm going to skip over this one because it's a little bit more complicated. So just next. Wait, go back. Yeah, this one. Okay. So this one here. The other thing that's very important for magnetic nanoparticles is their use in either magnetic resonance imaging or magnetic particle imaging. That's a new method that's gaining strength. The big problem with these methods is what they're using. And there's a lot of research being done here. There's a lot of controversy, and it's very hard to get these drugs certified for use, for human use. For many years, the reference material was a material called Coercivity. It was being used in the very first MRI studies. And in around 2000, they pulled it from the market because the trouble is it was made out of iron oxide. And iron oxide is very toxic to the body. So it's a real art to try to find a material that's going to be low toxicity to the body, but having the magnetic properties that one needs to have for the contrast. Okay, so the idea is you want something that's going to give you a very high contrast so that you can see a tumor or other features, but you want to have low toxicity. Okay? And maybe what you can see here, we work together with a little startup company in Berlin who are making a product called FairySpin. And their main product is called FairySpin R. And based on the hysteresis loop, you can see they're all closed loops. So they're all superparamagnetic. But what you can see different is you can see different slopes. So they took their product R and then they try to do a grain size separation. So they have a FairySpin XS, extra small, a FairySpin M, medium, and a FairySpin large, extra large, XL. And what you see is, if you go to the very small particles, you can see the slope is lower than if you go to the very large particles. So the larger the particle, the steeper the hysteresis curve is, okay? And if your curve, if you have a very high slope, that means you have a high susceptibility, which means it's going to react very well, easily to a field. Okay, next. So first we thought, okay, if we wanted to distinguish these to try to decide which one would be the best for predicting performance, we first looked at Forc diagrams. Because they're super paramagnetic, the Forc diagram, everything's at the origin. But one thing you can see, the Coercivity and the R, it's all shifted up above the zero, the main point, which shows it's super paramagnetic. The finer the grain size, the higher the shift up above zero. But in practice, this wasn't very diagnostic for saying how good the reflectivity or the product would perform. So next. So then we tried another method, and this is called field-cooled zero field cool. You take a sample, you cool it down in zero field to about 15 Kelvin, then you apply a very weak field, and you measure essentially susceptibility as a function of temperature, starting at 15 Kelvin up to room temperature. Then you cool it down again in a field, a strong field, 1 to 2 Tesla, or 5 Tesla, and then you warm it back up in a very weak field again, 50 millitesla, and you look, or 5 millitesla, 10 millitesla, and you measure the susceptibility. Now what's interesting is where these two curves split, this is telling you about where blocking, when the samples are starting to undergo blocking. So remember, for magnetite, on a scale of, let's say, 1 second, your blocking volume is going to be about 25 nanometers. So if we're close to 25 nanometers here, you can see this is blocking almost at room temperature right up here. Those curves start to diverge very close to room temperature. When we go to the medium, you see we have to get down to almost like about 160 Kelvin before they start to split. So we're only going to start blocking, you're only going to start magnetizing those fine grains by about 160 Kelvin. And for the very fine particles, we're almost down here around 50 Kelvin before they start to undergo blocking. And if you look at the normal material Coercivity and FairySpin, you can see the FairySpin normal product is very dominated by the larger particles because they have the highest susceptibility. And the Coercivity, you can see, is more like the medium particle here from of the product FairySpin. Okay, next. And what we did is we did two things. We first took the initial slope, so just in very low fields, what's the slope of the hysteresis curve? We saw the small particles had very low slope, the large particles had the highest slope, but everything in the middle sort of fell here. So it was diagnostic. It sort of said, oh, and this here is R2 over R1. These are the reflectivity ratios that you use in MRI to tell about contrast. The higher this ratio, the better the contrast. And sure enough, the one with the highest susceptibility has the best contrast. The one with the lowest susceptibility has the least best contrast. But in the middle, it sort of folded. And we were disappointed by this. But if we plotted it against the temperature at which these two curves separate and start undergoing blocking, we found a nice linear relationship. And we actually suggest this is a very good parameter to use if you're developing a drug and for MRI or MPI, and you want to know what its performance is going to be. Okay, next. Environmental sciences. I have two examples here next. One is carbon nanotubes. So this was a project we did with the University of Seoul and the University of Copenhagen. Now a nanotube, a carbon nanotube, has the advantage, if you can imagine that's hollow, it has a very, very high surface area. So these things are very ideal if you want to put some sort of chemical or enzyme on it to attract a pollutant. You have a high surface area so you can absorb a lot of material, pollutant. And so these carbon nanotubes are being used extensively, or being developed for use for things like soil remediation or water remediation. And then the idea is, once you put these carbon tubes in, you want to also be able to take them back out of the system. So the idea is to combine them with magnetic nanoparticles so that you can magnetically then separate out the magnetic nanoparticles in the carbon tubes and the pollutant. One of the problems is to actually put magnetic nanoparticles into these carbon tubes almost generates as much wastewater and contaminants as in using them. So you sort of like, okay, we make a good product for removing contamination, but we actually create another problem on the other side. So this group here, they said they didn't make their carbon nanotubes, they just ordered them from different manufacturers. I think they had one manufacturer in China and one manufacturer from Japan. And they said they noticed that there was already something magnetic material in them. So these are the carbon tubes, and you can see there's these nice little sort of superparamagnetic grains of some magnetic material in there. So they wanted to know, first of all, what was that material, and then how could they use it? Okay, next. So to look at what was in that material, we used the Curie temperature. So looking at susceptibility as a function of temperature here, you can see it drops very suddenly around, so we have something with a Curie temperature of 170 degrees Celsius. We see a little bit bump here that would be typical of magnetite, another one up here which may be maghenite. And then coming back, we lose a lot of this material in here, magnetite again. But the most material in there is, again, this cementite, this iron 3 carbon. So we said, okay, that's the magnetic material. Okay, next. First, they just took their nanoparticles as they got them, and they used them to try to absorb out the pollutant, and the absorbency wasn't very high. So they were a bit disappointed, but then they said, okay, why don't I just separate out the really strongly magnetic material and then check how that looks if we use the strongly, and they found the absorption was very good if they took only the strong magnetic material, and so they wanted to document the difference. So we measured hysteresis and Forc diagrams. You can see the Forc diagrams look the same for both. You have something here that's blocked, and you have something here, again, the superparamagnetic part. What you do see, though, is without separating out the strong magnetic material, just the material in general has a saturation magnetization that's going to be on the order of 0.2 ampere meters squared per kilogram. But if they pick out the more magnetic ones, they go up by a factor of 10. So we're up at around 2.5 ampere meters squared per kilogram. So they found that worked very well. Okay, next. And then just for one last quick example, I went over my time. I should stop. Okay, now I should stop. Anyway, just a very quick example. This is a gold mine in Bulgaria. The mine is abandoned, but they had the tailing ponds there, and at one point the tailing ponds actually broke. And the material got distributed down the river. So it came down the river. There's a little lake here with a dam, and then below the dam it flows into the Danube River, one of the biggest rivers in Europe. And they wanted to know, the trouble is to get the gold out, of course, they have to use arsenic. And they wanted to know, okay, is arsenic contaminating the soil? So the soil chemistry professor, Ruben Kretschmar, had a student working on this. Next. Okay, we looked at iron as a function of susceptibility in these soils. And you can see there's a very distributed distribution of susceptibilities going from very low to very high. It was very interesting. You saw iron would remain at 4 weight percent, but you would still get a pretty big range of susceptibilities. And it was only after you went up above about 1 times 10 to the minus 5 that you actually started to get a nice linear relation. Next. This is where, from the mines, this is from the part directly where the tailing ponds had broken out. And next. And these are samples that are further away from the river. Okay, next. Now, more interesting is when we plotted the susceptibility as a function of arsenic, because there's no natural background for the arsenic as there is for the iron, so we think this 4% is just the natural background in the soils. But with the arsenic ratio, we saw arsenic as a function of susceptibility. You have this nice linear relationship. Again, next. You can see the mine here, the tailings here. Okay, next. We found that the material on basis of the Curie temperature and the Vervet transition is magnetite. Next. And then by doing profiles across the river, we could see here, you can see iron peaks right at the river. Is lower on the upper side of the river where the land is a little bit higher. And on the lower side where you can get flooding, you do see a higher iron content, you see a higher arsenic content, and you can also see from the susceptibility a little bit higher. So the idea is they could then take more samples, measure susceptibility, and get an idea of the arsenic content. Okay, thank you. So in summary, in the material and life sciences, one can use them to verify composition, one can monitor concentration, and one can also look at it to look for particle size. And I always say it's a give and a take, because we measure rocks, and we come up and we write these books and we say magnetite should look like this, but we really don't know what it should look like. So it's really when we get materials that are very pure, with a very well-known grain size, we can actually use that as a calibration for us to know what to expect when we look at a rock. Okay, thank you.
Thank you very much, Professor An, for the very nice and experimental reports and presentation. If you have any questions, ladies and gentlemen, questions are welcome. Pak Nanda.
Okay, thank you. It's very nice talks. And my question is, maybe I slightly miss about the how to distinguish between superparamagnetic and, for example, in magnetite is normally is very magnetic, correct? Yes, I think between superparamagnetic and paramagnetic from hysteresis loop. Okay, and second is it possible as well to distinguish this superparamagnetic and for example in the paramagnetic in the paramagnetic regime, and the third is I seen in the last slide you saw there is a good correlation between iron and arsenic magnetism, but in general that arsenic is not magnetic. There is no magnetic moment, and etc. etc. And how is the correlation between arsenic and iron in general? Because
I'll start with the last one. That's an excellent question. What is the relation between arsenic and magnetism? Because it's not. And actually, I told several people here, I tried about 5 years ago to get money through the Swiss Science Foundation to actually have one of Satria's former students come to Zurich and have a joint doctoral student. Unfortunately, we didn't get the money. And at the time, we really didn't understand why is the susceptibility replacing arsenic. In the meantime, in the last couple of years, there's been about 2 or 3 papers that have come out to say that arsenic binds with iron hydroxide. Now, iron hydroxide has a fairly high susceptibility. It's not as high as magnetite, ferrimagnetic. And so what we think is happening is the arsenic is binding with the iron hydroxide, and that's why we're seeing a good correlation. Where when we look at iron, we have this one sort of plateau, 4% iron, and that probably has the magnetite and other minerals in there. Okay, now about superparamagnetic, paramagnetic. If you have a paramagnetic material, your hysteresis loop is going to just be linear, positive slope. If you have superparamagnetic, let's say above 3 nanometers, you will actually get saturation. If you go down very, very small, they probably will not saturate. So it's a question of volume of the material versus surface area. So above 10 nanometers, your volume is bigger than your surface area. When you get below 10 nanometers, your surface area starts to get bigger and bigger. So if you have a high surface area, your spins don't line, you have these uncoupled spins, and so it'll look paramagnetic. But I would say what we notice is as long as they're certainly 5 nanometers or larger, you will see a very steep slope and you will see saturation. But what we find is if you're close to the boundary between single domain and superparamagnetic, the slope is very high, and as it gets smaller and smaller, the slope becomes less, and it's partly because of those uncoupled spins at the surface. You can't saturate those magnetization. Okay? Does that answer your question? What is the slope for super? You can't say. That's the problem. I mean, this is the big. And I'll tell you. This is where the real part comes in. So, what other material has a closed hysteresis slope? The students? Anybody want to answer that? It's an exam. So, multi-domain. Because if you have multi-domain material, the hysteresis loop will also be closed. So it's very hard to tell, is it multi-domain or is it superparamagnetic? And the only way you can distinguish those two is if you can measure hysteresis as a function of temperature. Because if it's superparamagnetic, if you go colder and colder, you'll start to actually lock in those spins, and then you will actually see the loop opening up. So if you see the loop opening up, then you know it's superparamagnetic. And if it's multi-domain, you can cool down and it won't change. Okay?
One more question, please.
Anyway, thank you.
Okay,
sorry that it was a little long.
Thank you very much, Professor Ann. And now we can conclude that rock magnetic techniques is extremely essential for material science and life, as well as environmental sciences. Thank you once again. Please give a round of applause to Professor Ann. And